All right, so these videos are just kind of supplemental to the Chapter 9 videos, and they're all about kind of working through some of these examples and using confidence in action. And so all I've kind of done is I've gone through some of the homework problems in the book, not the ones I've assigned, unfortunately. I'll let you do those. But some of the other ones that use the same methodology as the ones that I've assigned. So if you work through these or you watch these and you work through those, you should find a lot of similarities. And then the goal is you can do other problems like this. Okay, so what this is talking about is this is number 26 from the book, and it's savings for retirement. And the question says we have a survey of 1,153 workers and retirees. They're all from the US, and they're all 25 years or older. And this was taken in January 2010, and it was taken by the Employee Benefit Research Institute. So what they found was that 496 had less than $10,000 in savings. So this was their savings for retirement, or their total savings probably. So what we want to do is part A says find a point estimate for workers and retirees in the US 25 years old or older with less than $10,000 in savings. B, verify the requirements for constructing a confidence interval. So we want to remember what those requirements are. And C is construct a 95% confidence interval. And D, interpret the interval. Okay, so what I'm going to do is I'm going to grab my calculator. And I'm going to come over here, and for A, if I want to solve this, what I'm going to do is I just need to find a point estimate. Well, the point estimate is to take the sample we found and figure out the proportion for that sample. So we have 496 had less than 10,000 in savings, and we took a sample size of 1153, and then when you work that out, what you'll get is for 96 divided by 1153, you get 0.430. And that's out to 3 decimal points, which is going to be perfectly fine. And this is going to be our point estimate. We're going to call it p hat. Now remember, when we're talking about p hat is both our point estimate, and we also think about it as a random variable. Variable based on sample distributions. Okay, so B is verify the requirements for constructing a confidence interval. So what are the requirements for constructing a confidence interval? Well, we actually just have two. We have to make sure independence is satisfied, and then we have to make sure that our sample size is large enough. So independence and large enough sample size. And so how do we verify the independence? Well, we have to check that our sample size is less than 5% of our total population. Well, what's our total population? Our total population is going to be 25-year-olds or older, so people who are older than 25 years old, who are workers and retirees in the US. That's probably going to be well into the millions. So we can reason that a sample size of 1153 is definitely going to be less than 5%. So independence is satisfied. We're okay with that. But you do have to give a reason for it. So you can't just ignore that part because maybe your population is actually a lot smaller than you thought. So you should give time to think through that. Okay, independence is satisfied. Now, is our sample size large enough? So it's kind of funny, this interplay. We want independence, so we want our sample size to be small enough, but we also want it to be large enough. And this is so we can assure that the central limit theorem works. Well, the limiting aspect of it, so the growing of the n. Okay, so what we're going to do is remember large enough when you're dealing with p hat, it means that we want n, our sample size, times p hat times 1 minus p hat to be greater than or equal to 10. Well, how do we work that out? Well, we plug it into our calculator. So we have 0.43 times 1 minus 0.43 times, what's our sample size? Our sample size is 1153. And that's going to be 282, 282.6, which is definitely larger than 10. So that works out. So it's definitely large enough. And maybe you're thinking, like, I knew that. I could do that calculation in my head. Okay, well, it's good to do it in the calculator too. So you get verification. All right. So now we want to construct a confidence interval. So this is where things get kind of interesting, is we want a 95% confidence interval. So we have that our confidence is going to be equal to 0.95. And what we want to do is we know that our error is going to be, well, it's just going to be some z sub alpha over 2 times standard deviation of p hat. Now, this is where we're interpreting p hat as a random variable, because we want the standard deviation of the random variable, which is population proportion or sample proportion. And so remember that the standard deviation of p hat is just going to be p hat 1 minus p hat over sample size. And you might be thinking, well, why are we using p hat? Why aren't we using the actual parameter? Remember, we don't know what the actual parameter is. So this parameter here, this guess for a parameter, is the best that we can come up with. Okay? Now, how do we find the z sub alpha over 2? Well, that's going to be determined by our confidence. If you pick a confidence, then you can find what the alpha is. It's just going to be 1 minus the confidence. And so our alpha is equal to 0.05. And so if you divide that by 2, alpha over 2, you're going to get 0.0025. Sorry, I put an extra 0 in there. And so what we're looking for is we're looking for the critical value, z sub 0.025. And so what we want to do is we want to remember what that means. So what it means is if you look at the normal standard distribution, it's going to be the z value where to the right of that value, this area is 0.025. This is the area. So now we have to look up on table 5 for critical values where the area is equal to 0.025. And one thing you might come up with is you might find that the z sub 0.025, the best estimate is going to be 1.96. So that means this value here is 1.96. So if we look at that, that's the z value you're going to do. And so what we come over here and do is we figure out our error. It's going to be 1.96 times whatever this gross value is here, and it's just going to be the square root of 0.43 times 1 minus 0.43, all divided by 1153. And if you plug that into your calculator, as I did before this, you'll find that the error is going to be 0.0286. Okay, so what does that mean? Well, it means that our confidence interval is just going to be our point estimate minus some error to our point estimate plus the error. So remember, we're going to take this error and we're going to subtract it from our point estimate, and we're also going to add it to our point estimate. And that's going to be the confidence interval. And so if you use the point estimate that you found and you use this error that you found, what you'll get is 0.401 to 0.459. And I've rounded it to 3 significant figures. So that's going to be the confidence interval. And so remember, the confidence interval is the interval where the length of it, if you use similar intervals with the same length and you come up with different point estimates, different sample sizes, you're going to capture the actual parameter 95% of the time. So this actually goes to the interpret the interval. What does this interval mean? It means that if you were to use an interval of that same size and you were to use different point estimates kind of surrounding it, so you use the same error and different point estimates, you would capture the actual parameter 95% of the time. At least we have kind of probability backing that up. Okay, and so what you might also think is going back up to this, it means that we have 95% confidence that the number of workers and retirees who save or who have less than $10,000 in savings is somewhere between 40% and 46%. So you could say that. So that's we have a certain level of confidence that the actual parameter is somewhere in there. All right, so the next example we have is about home ownership. So this is again from 9.1, and it's number 36. So the setup is that we have an urban economist. They wish to estimate the proportion of Americans who own their homes. If they wish to estimate the estimate to have 90% confidence with an error no more than 0.02, then how large should their sample be if, and we have two parts, they use a 2010 estimate of the parameter being 0.669 from the US Census Bureau, or B, they do not use a prior estimate. So we have to remember that there are two possible cases. There's the using prior estimate cases, and then there's the no prior estimate cases. And if you're ever working with something and you're kind of unsure about your prior estimate, it's always good to go with the no estimate case, and we'll talk about that in a second. Okay, so for A, what you want to do is you want to say, well, you remember your sample size should be n, and that's going to be equal to p hat 1 minus p hat times z sub alpha over 2 divided by error, all of that squared. Okay, so this is a formula. What does it mean? So remember, the idea is we're given a confidence, we're given an error, and if you know those two things, you can actually solve for your n in the equation for a confidence interval. So, or the equation for the error. You can solve for the n. And that's what we do to come up with this formula. And once you solve for the n, then you can think, well, if I know a previous parameter, and I know what my error should be, and I know what my confidence should be, well, I can find this critical value if I pick a confidence. Remember, the confidence determines the critical value, and I can determine this n. And all that's left is you have to recognize that sometimes this n isn't going to be an integer, so you just need to make sure to round up. Okay, so we just need to figure out these things. Well, in part A, we're going to be using this p-value to be our p hat, because this is our prior estimate. And our error, our e, is going to be 0.02. And how do we find our z sub alpha over 2? So this takes a little more effort. Well, we have to remember that our confidence, we want that to be 90%. So that's going to be 0.90 or 0.90. And our alpha is just going to be 1 minus c, so it's going to be 0.10. And then our alpha over 2 is going to be 0.05. And so what we're looking for is we're looking for z sub 0.05. And here's something interesting. If you look on the table in section 9.1, you'll see that they have this number written, 1.645. And you might be thinking to yourself, how do you get a critical value out to 3 points or out to 3 decimal points? Because if you're using table 5, they only give it to you out to 2. Well, if you look up on table 5, they're actually not going to give you critical points for z sub 0.05. They have one listed for 0.0505, and they have that listed at 1.64, and z sub 0.0495, and they have that listed at 1.65. And notice that these are an equal distance away from 0.05. So either one of these is a good option. So what the book is doing is it's taking the average of these two. And it's saying you can do it that way. So this is going to be equal to 1.64 plus 1.65 divided by 2. Now, this isn't completely a correct way of doing this, but because these are estimates anyway, that's okay. And we're going to be talking about, I'll tell you what you can do in a second to like make sure that it's completely okay. But either one of these would be fine if you're working through this problem and you get a little bit of a rounding error because you're using these estimates instead of this one. But when the book computes the answer, if you're comparing it, they're going to be using this because they're taking the average of these two. Okay, so now we have our z value, our e, and our p hat. We can just plug these in and find our n. So our n is going to be, let me plug them in. So you have 0.669 times 1 minus 0.669 times 1.645 divided by 0.02, all of that squared. And if you plug that in, you're going to get 1498 point something, I think like 0.49. It doesn't really matter because you round up to 1499. Why do you round up? Because you can't use point of some person, and as long as you're making this n larger, you're going to stay within that error. So maybe your error isn't going to be quite 0.02, but if you increase your n, if you just make it bigger, it's always going to lower that error. So it's always going to stay within that error. So this is actually where you might be thinking, well, which one should I use? Just use one of them and maybe bump your sample size up by 100 or something like that. It depends exactly on what you're working with, and it depends what your answers are. But if you're getting something in the thousands range and you're worried that it's giving you too low of a sample size, just bump it up 100 more. I don't know. You can't do that on tests. I'm going to be looking for kind of the minimum value. But when you're working in real life, you can always add a little bit more to your sample size. Because remember, the idea is if you make your sample size larger, the error goes down. Okay, well, what do we do for B? Well, what B is saying is we're not going to be using a previous estimate. So let's look at this equation here. Okay. One thing to keep in mind is we have kind of these two parts. You have this thing here and you have this thing here. This is fixed once you choose your confidence and your error. If you have your error here and you have your confidence, this number is set. This thing here is what is depended on by your previous estimate. This is the p hat. So what we're going to do is we're going to analyze this and we're going to say, well, if we don't have a prior estimate, let's just use the highest possible value that could possibly come about. So what I mean is, when is this term largest? Because that would be the safest thing to use. Well, if you look at the equation x times 1 minus x, and you look at y equals that, you're going to get a parabola, and it's going to look like this. So you could plug this into a graphing calculator. And parabolas always have a highest value when they're flipped like this. So they either have a highest value or a lowest value. In this case, you're going to get something that's concave down, and so it's going to have a highest value. And so what you want to do is you want to figure out what that highest value is. Well, with a little bit of calculus, you can find that it's going to happen when x is 1/2. So this is going to be 0, this is going to be 1. You're going to find it when x is 1/2. And so what the highest point here is going to be is when x is 1/2, and y is going to be 1/2 times 1 minus 1/2, which is going to be 1/4. And so the largest this thing can be is 1/4. That's why they say if you don't have a prior estimate, just use 25% or 0.25 for this thing here. Because what this is going to do is it's going to give you the largest n once you've already fixed your confidence and your error. Okay, so if you plug that in, so if we do 0.25 times 1.645 over 0.02 squared, you'll get the n should be, I think 1691.2 whatever, but you round up and you get 1692. And again, it's important that you're rounding up. You're not rounding to the nearest integer. You're always rounding up. And that's just because if you round down a little bit, you might move yourself to a larger error. Okay, so now we're going to talk about 9.2, which, remember, that's all about t-distributions. So we're going to see how it's going to change our answers to problems. We're still going to be constructing confidence intervals, but the setup is a little bit different. We're going to be working with the population means, so we're going to be estimating the parameter of a mean, and we're going to be using the sample mean as our random variable instead of the sample proportion. Okay, so this question is number 28, and it's titled Hungry or Thirsty. It comes from 9.2, and the byline is, how much time do Americans spend eating or drinking? So I'm going to read it out. Suppose for a random sample of 1,001 Americans age 15 or older, the mean amount of time spent eating or drinking per day is 1.22 hours with a standard deviation of 0.65 hours. So notice my n, my sample size, is 1,001. The sample size is going to be a lot more important when we're working with t-distributions. The x, or the sample mean, is 1.22 hours. And the sample standard deviation, remember we're using a sample standard deviation, is going to be s, and that's going to be 0.65 hours. And question A and question B kind of ask the same thing. They're asking, how can we use normal distributions to help interpret this problem? So A says, a histogram of the time spent eating and drinking each day is skewed right. Use this result to explain why a large sample is needed to construct a confidence interval for the mean time spent eating and drinking each day. So if you're thinking about data that's skewed right, you would need a large sample size in order to make sure that what we're doing is kosher. Again, this is all just how do we make sure the central limit theorem kicks in. The central limit theorem says that the sample mean distribution will be approximately normal no matter what the underlying distribution looks like, as long as your sample is large enough. Okay, so, and then B says there are over 200 million Americans age 15 or older. Explain why this, along with the fact that the data were obtained using a random sample, satisfies the requirement for constructing a confidence interval. So again, confidence intervals, there are two requirements always. Does the central limit theorem allow us to say that the sample distribution is normal? Yeah, as long as your n is large enough. Now, the second criteria is, do we have independence? So always central limit theorem and independence. Well, how do we verify independence? Well, this is kind of a rule of thumb. As long as your sample size is less than 5% of your population, which we were just told is 200 million, then yeah, our sample size is much smaller than that. So what we can do is we can go ahead and use our sample and construct a confidence interval. So remember, confidence intervals are built on this assumption that we have this normal distribution. And yes, t distributions aren't exactly normal, but they're close to normal and they approximate the normal, and we can adjust for that. Okay, so C is where it really kicks in. We want to determine and interpret a 95% confidence interval of the mean amount of time for an American 15 years or older who spends eating or drinking per day, or the mean amount of time that American 15 years or older spends eating or drinking each day. Okay, so how do we do this? Well, we want to find our confidence interval, which is just going to look like this. It's just going to be our x bar minus some error, our x bar plus some error. So remember, your point approximation is going to be in the center of this interval, and then you're going to have that minus your error and that plus your error. And how do we find the error? And that's all it boils down to, is we have to find the error. But remember, when you're working with a sample mean, you have to use the t distributions. So you have to use t alpha sub 2 times s over n. Remember, this is just t sub alpha sub 2 times our standard deviation. But how do we find this t value? So we know what this is. We know what this is. How do we find the t value? Well, the t value is going to be determined by, we have to find the alpha. Well, if we want our confidence to be 95% or 0.95, then our alpha is going to be 1 minus the confidence, or 0.05, and alpha sub 2 is going to be half of that. And we also have to figure out which t distribution we're using. And that depends on what? Depends on the degree of freedom. So we have to figure out what the degree of freedom is. Well, remember, the degree of freedom in this case is just going to be our sample size minus 1. So our degrees of freedom are going to be 1,000. And so if we look at table 7, in the degrees of freedom equal 1,000 row, and then we look in the column for 0.025, we find that t sub alpha 2, or alpha divided by 2, which is t sub 0.025, is going to be 1.984. And you might actually see that this is actually very, very close to the z value at this point, to the critical value of z at 0.025. But even though it's pretty close, that's because you're using a very, very large n. So remember that the t distribution, as that n gets very, very large, it starts approximating the actual standard normal distribution. So that's why you're getting something very, very close to that. But still, we want to use this value here. Okay? Well, if we plug that in to this error, we use this value here, 1.984 times our sample standard deviation divided by the square root of 1,001. What you'll get is, you'll get that this is going to be approximately 0.040. And then if we figure out this interval here, what you're going to get is you'll get 1.180 and 1.260. So that's the interval that you're going to do. Okay, so how do we interpret it? Well, what we say is that we have 95% confidence that the mean amount of time an American that's 15 years or older spends eating or drinking per day is going to be about 1.18 hour to 1.26 hours. And what we mean by 95% confidence, again, is that if we were to construct intervals using these same methods, using random choices of individuals, and they were all the same size, we would capture our parameter 95% of the time. Our actual mean time would be within that 95% of the time. So remember, that's what confidence means. The last little bit of this question asks, well, what it asks is, would it be okay, so there's a D part, would it be okay to use this same thing for 9-year-olds and older? So let me just make sure I'm stating that correctly. So it says, could the interval be used to estimate the mean amount of time a 9-year-old spends eating and drinking each day? Explain. And it's not going to work out because you're using a different population. And what does that screw with? Well, it's screwing with the randomness. Because what you're using is, we can't use this because we've made sure to choose all of our people outside of the 9 to 15 range. And so this isn't a random sample anymore. So you can't use it for a different population because that screws with the randomness. So our assumption that that it's randomly chosen is off the table. All right, so this is our last example. It's about reading, and it comes from 9.2. And the idea is we're going to determine the sample size we want to use if we pick an error and we pick a confidence. So remember, if you pick those two things, you can figure out what the best sample size is to use to ensure that your error stays within that, within those bounds, and your confidence stays up. So what we have is a recent Gallup poll asked Americans to disclose the number of books they read the previous year. Initial survey results indicate that the standard deviation is going to be 16.6 books. That seems pretty large. Let me make sure that I have that right. Yeah, I guess that's the standard deviation, 16.6. All right, so part A is how many subjects are needed to estimate the number of books Americans read within 4 books. And what we want to do is we want to keep our confidence at 95%. Okay, so to answer this, remember that if you wanted to find the error is just going to be, well, it's going to be t sub alpha over 2 times your sample standard deviation, or the standard deviation of your sample, divided by the square root of n. And what we're going to do is we can solve for n by flipping all of this, and we're going to get square root n over s times t sub alpha over 2, which is equal to 1 over e. And then you can solve for the square root of n and get s t alpha over 2 all over e. And then if you square both sides, you're going to get n is going to be s times t alpha over 2 all over e. Now, what we're doing here is, notice, remember from last time, this t-value depends on what n you've chosen. So if you haven't already chosen that n, it doesn't make sense to say what the t-value is. So what we're going to do is we're going to assume that we're getting close enough that our t-value is actually going to be well estimated by the z critical value. And that z value is fixed. Once you have a confidence, you can figure out that z value. You don't need to know your sample size. You don't need to know the degrees of freedom or anything like that. It's degree of freedomless. You don't need that. So what we're going to do is we're going to use, this should be all squared. We're going to use this. And we're just going to figure out, well, if E is 4 and S is 16.6, and we want our Z value at alpha is 5%, or alpha is 0.05, so our Z value is 0.025. Remember, that's 1.96. So we used that last time. And so we're going to use 1.96. This is a 6. And that's going to be your n once you square it. And what you'll find is, let me grab the calculator. And you'll get 16.6 times 1.96 divided by 4. And if we square that, you'll get that n is equal to 66.16. And again, you round up, and so we're going to get 67. That's the sample size we should use. Okay, what if we wanted to do it within 2 books? Well, how is that going to affect our value? What we do is we're going to use the same formula, but this time our error is going to be 2. And what we're going to get is, so this is 16.6 times 1.96 all over 2. And you're going to square that. That's going to be your n. And that's going to be n equals 264.64 dot dot dot. Doesn't really matter, you're just going to round it up. And what you notice is when we want to cut our error down, this thing is going up. And in fact, when we cut our error in half, what actually ended up happening is this ended up quadrupling. The sample size that you needed actually ended up getting a lot larger rather than just doubling. And that comes from the fact that the error is down in the denominator and you're squaring it. So when you double the error or cut the error in half, what it's actually going to do is it's actually going to double that, and you get a quadruple on your number.